In this lab, we're going to be finding the activity series of metals which involves single replacement reactions. If you look at the page in your packet on lab activities of metals, you're going to see a bunch of different reactions written that are single replacement. So here you see aluminum, and it replaces copper in a solution. So the aluminum kicks out the copper, and now the aluminum goes with the chloride, and the copper is left by itself. The same thing would happen with magnesium and hydrochloric acid. So magnesium can kick out the H, so the magnesium goes with the chloride and the H is by itself. And don't forget that when H is by itself, it has to be written with a 2 for Hanaff-Gilbriat. Another example is potassium kicking out an H from water, so the K goes with the OH and the H is by itself. Again, the H has to have a 2 because it's diatomic. Now, if we look down at the bottom of the page, this is going to show you how we're going to figure this out. Okay, on the left side, you see solids. So element A, B, C, and D are all solids. And then here are solutions of A, B, C, D, E, and F, and these would be aqueous. So you could see that the top row is going to be aqueous, and the sides are going to be solids. So what happens is, if you put a solid into an aqueous and it has a yes, that means it reacts, that means the solid kicked out the aqueous. That's what's happening over here in the magnesium. You can see the magnesium solid, it kicks out the one that's aqueous. So now the magnesium becomes aqueous, and the other one becomes either a solid or a gas, in this case a gas, whereas if you look up ahead a little bit, it became a solid. Okay, so the one by itself will be whatever it is. In real life, copper is a solid, hydrogen is a gas when it is by itself. So we're going to take a look at this chart and we're going to find out all the yeses. Let's find the element with the most yeses. So the element with the most yeses in this, let's count. The A has 1, 2, 3, 4. The B has none. The C has 1, 2, 3, and the D has 1, and that's it. So the one that has the most activity is the A. So out of all these 4, the A is the most, the B is the least out of these 4, and then we have C is the second most, and D is the third most out of all these. The way we know that is because A has 4 yeses, so it's at the top of the list. C has 1, 2, 3 yeses, so it's next. D has only 1 yes, so that's over here. And the B has none, so that's last. The funny thing is that I didn't give you any information about F or E on the left side. I didn't give you any solid F or solid E. In real life, the reason is perhaps that there is no solid version of these. Maybe they exist as gases. So F and E do not have any data. So let's figure out something. You'll notice that nothing could kick out F. A could not kick out F, B could not kick out F, C could not kick out F, D could not kick out F. So if nothing could kick it out, that means it must be the most active. Nothing can kick it out. So that means that F must be at the top of the list. And then let's look at E. E was kicked out by, oops, sorry about that. E was kicked out by A and by C. So A and C kicked it out. So E was kicked out by A means A is more active. And it was kicked out by C, that means C is more active. However, D could not kick out E. D could not kick out E. So therefore, D is weaker than E, or less active. So therefore, the E must fit right over there. So E is going to fit right here. So the final order is going to be F, A, C, E, D, B. That's the activity series of these fictitious elements. So what you'll do in this lab is very similar to what you did in the double replacement lab, where you're going to be testing the reaction of Fe with every other solution, and then copper with every other solution, etc. And you're either going to write a yes or a no. All right, so if there was a reaction, you'll write yes. If there was no reaction, you'll write no. And you're going to do that for all of these boxes. And once you do that for all these boxes, you'll be able to recognize which of these metals is the most active and which would be the least. Also, we are going to try doing this on the paper with the transparency plastic sheet over it. If that doesn't work, then we'll try it in those wells that we learned to use the other day. Lastly, we're going to learn how to write three types of equations, which we were exposed to these before. The complete molecular single replacement, which is the regular single replacement we learned how to write, and the complete ionic, which is a new one for us, and then the net ionic, which we've heard of before with the double replacement. So with the complete molecular single replacement, we write it as we learned before. The aluminum, in this example, would kick out the silver to go with the nitrate. So aluminum, nitrate go together. Silver's by itself. And if you work on your charges, you'll remember that Ag is +1 from your polyatomic paper. Nitrate is -1. My nitrate is -1. You know aluminum wants to be +3. So therefore, that's the formula for each one. So first you write the formula correctly to be neutral. The elements are by themselves right here. And then after that, you work on the coefficients. So this would be a 1. This would be a 3. You don't have to write the ones. This would be a 1. And this would be a 3. Okay, so now what we do is we write what's called the complete ionic equation. The complete ionic equation is going to be when you break up all aqueuses into ions. So the aluminum solid stays the way it is. There are 3 Ags total here, so you write 3 Ag plus aqueous because they're dissolved in water. And there are 3 nitrates altogether, so you write 3 NO3 minuses, aqueous. On the right side, you got 1 aluminum right here, so you just write that Al plus 3 aqueous. And you got 3 nitrates altogether, so that's going to be 3 NO3 minuses aqueous. And then you just copy down the 3 Ag solid. Lastly, you look for what we call spectator ions. Spectator ions are exactly the same on both sides. So see how the 3 nitrates on the right and 3 nitrates on the left are exactly the same? So those are called spectator ions. Just like a spectator at an event is just watching, that's what these do. These are the ones that are going to be eliminated for the net ionic because nothing is happening to the nitrate. So what's really happening is aluminum has no charge. 3 silvers do have a charge and they're aqueous and they're +1. And then what happens is the aluminum gets a charge of +3 and goes aqueous, and then the 3 silvers become no charge and they're solid. And this is how you're going to write each of these parts A, B, and C for your lab. And you're going to do this just for the magnesium reactions.